Cauchy's theorem, group theory. In mathematics, specifically group theory, Cauchy's theorem states that if G is a finite group and P is a prime number dividing the order of G, the number of elements in G, then G contains an element of order P. That is, there is X in G such that P is the smallest positive integer with XP equals E, where E is the identity element of G. It is named after Augustin-Louis Cauchy, who discovered it in 1845. The theorem is related to Lagrange's theorem, which states that the order of any subgroup of a finite group G divides the order of G. Cauchy's theorem implies that for any prime divisor P of the order of G, there is a subgroup of G whose order is P, the cyclic group generated by the element in Cauchy's theorem. Cauchy's theorem is generalized by Sylow's first theorem, which implies that if Pn is the maximal power of P dividing the order of G, then G has a subgroup of order Pn, and using the fact that a P group is solvable, one can show that G has subgroups of order Pr for any r less than or equal to n. Statement and proof. Many texts prove the theorem with the use of strong induction and the class equation, though considerably less machinery is required to prove the theorem in the abelian case. One can also invoke group actions for the proof. Proof 1. We first prove the special case, that where G is abelian, and then the general case. Both proofs are by induction on n equals G and have as starting case n equals P, which is trivial, because any non-identity element now has order P. Suppose first that G is abelian. Take any non-identity element A, and let H be the cyclic group it generates. If P divides H, then H/P is an element of order P. If P does not divide H, then it divides the order G, H of the quotient group G/H, which therefore contains an element of order P by the inductive hypothesis. That element is a class XH for some X in G, and if M is the order of X in G, then XM equals E in G gives XHM equals EH in G/H, so P divides M. As before, XM/P is now an element of order P in G, completing the proof for the abelian case. In the general case, let Z be the center of G, which is an abelian subgroup. If P divides Z, then Z contains an element of order P by the case of abelian groups, and this element works for G as well. So we may assume that P does not divide the order of Z, since P does divide G, and G is the disjoint union of Z and of the conjugacy classes of non-central elements. There exists a conjugacy class of a non-central element of whose size is not divisible by P. But the class equation shows that size is G CGA, so P divides the order of the centralizer CGA of A in G, which is a proper subgroup because it is not central. This subgroup contains an element of order P by the inductive hypothesis, and we are done. Proof 2. Proof 2 uses. A practically immediate consequence of Cauchy's theorem is a useful characterization of finite P groups, where P is a prime. In particular, a finite group G is a P group, i.e. all of its elements have order Pk for some natural number k if, and only if G has order Pn for some natural number n. One may use the abelian case of Cauchy's theorem in an inductive proof of the first of Sylow's theorems similar to the first proof above, although there are also proofs that avoid doing this special case separately. Example 1. Let G is a finite group where x2 equals E for all element x of G, then G has the order 2 and for some non-negative integer n. Let G is M. In the case of M is 1, then G equals E. In the case of M equals 2, if M has the odd prime factor P, G has the element x where xp equals E from Cauchy's theorem. It conflicts with the assumption. Therefore, M must be 2. G is an abelian group, and G is called an elementary abelian 2 group or Boolean group. The well-known example is claimed 4 group. Example 2.